Hello everyone, welcome to Physics 11. We're starting a series of lessons about Physics 11 based on a Nelson textbook. Unit 1, Kinematics. Kinematics is organized in two chapters. First chapter is motion in a straight line, and second one is motion in two dimensions. Here are overall expectations. After completing this unit, you'll be able to analyze technologies that apply concepts related to kinematics, investigate linear motion and non-linear motion, uniform and non-uniform motion, demonstrate understanding of linear motion with a uniform and non-uniform velocity, and later on in chapter 2 with two-dimensional motion as well. Big ideas. Motion involves a change in the position time graph. We're going to talk about velocity time graph as well and acceleration time graph. Motion can be described using mathematical relationship, especially on 5 key formulas in the kinematics, and technologies that applies those concepts. Chapter 1, motion in a straight line. We're going to talk about all the concepts and all the relationship between different concepts in kinematics. And then in chapter 2, we're going to apply those in a two-dimension. Here are key concepts of the chapter 1, motion in a straight line. Explain how distance, position, and displacement are different. Obviously, distance is scalar quantity and position and displacement are vector quantities. And we're going to talk about vector and scalar quantities, how they are different. Then we're going to continue with the speed, velocity, and acceleration, how they are different and how they are related. Obtain motion information from position time graph, velocity time graph, and acceleration time graph, and how can we derive one from the other. Solve uniform velocity and uniform acceleration problems using algebraic method, as we call it as a 5 key equations of kinematics. Describe how acceleration due to gravity affect the motion of the object close to the surface of the Earth. It's very important to mention that close to the surface of the Earth, where the gravitational acceleration, it is related to the location where you are, depend on the location where you are, and know the technologies that applies those concepts. That's another very key important thing that we are going to focus on this chapter. Chapter 1, Section 1, Distance, Position, and Displacement. In this section, we're going to compare and contrast those 3 different concepts in kinematics. And we're going to see a difference between scalar quantity and vector quantity. In order to understand the motion of the objects, we must first be able to describe that motion. What happened in that situation? So kinematics is the term used by physicists and engineers to describe the study of how objects move. So it is a study of motion. So what is motion? Motion is the change in location of the object from the reference point as measured by an observer. And what is a reference point? It's a point used to find or describe the location of something. So reference point, most of the time, is where you put yourself in that location in order to describe what happened in that motion. Distance is a simple concept. A distance is a total length of path traveled by an object in motion. So the distance symbol is d, lowercase d, and a standard unit is meter. For example, what is a distance traveled by you if you start from your home, go to your friend's house, and then go to the grocery store? So you go from your house to your friend's house, you travel 2.1 kilometer, and then you go back another 2.1 kilometer, and then from your house to a grocery store, another 4.3 kilometer. So as we said is a total length. So every motion in any direction counts as a distance travel. So we have 8.5 kilometer travel. It is a very important in physics understanding to be able to distinguish between scalar and vector quantities. A scalar quantity is a quantity that has a magnitude or a size only. For example, time or mass or height. So you never question that those quantities about any direction whatsoever. However, a vector quantity has a magnitude, also direction. So the direction is very important in a vector quantities. An arrow is placed above the symbol for a variable when it represents a vector quantity. We're going to learn about the vector quantities in this chapter. How to add vectors? In order to add vectors, we can place a tip to a tail of the other vectors. So we can place one vector after the other. Direction of the vectors does matter. So let's say that we have two vectors, A and B, and we have to add them up, making the sum of two vectors as a vector C. How can we draw it? Let's say that we draw vector A first, and that vector A has to be proportional to its magnitude. So, and then immediately after vector A, we draw vector B. So where the vector A ends, vector B starts. So the start of the vector is called tail, and end of the vector, where the arrow is called tip. So we are talking about we place the tail of the vector B to the tip of the vector A. That's why it's called tip to tail method. Then we can actually, in order to add those vectors together, we can draw another vector which is a sum or a total of the two vectors. Then that vector has to be starting where the first vector starts, in this case where the A vector starts, and should end where the last vector ends. So it's going to be tip of the vector B, like this. As a matter of fact, direction matters because it's not you are just adding two vectors together as a magnitude only, but direction does have to be very important. So if you want to add a vector A and you have another vector B which happen to be the opposite direction of the vector B that we just drawn before, in opposite direction like this. So the rule is the same. You place the tail of the vector B where the tip of the vector A is. With other words, we can say we can place the start of the vector B to where the vector A ends. So we can place vectors one after the other, and as a total would be again the same rule. Start where the first vector starts toward where the last vector ends. So where the tail of the vector A toward tip of the vector B. So if you see very clearly, vector C, which is a sum of vector A and vector B on both cases, is totally different. It's different because now we are adding vectors. We are not just adding numbers. So the length of vector represents its magnitude. That means by looking at those two vectors A and B, for example, we know for sure that magnitude of vector A is bigger than magnitude of vector B. Why? Because vector A is longer, is drawn longer than vector B, and we know the vector C is longer than both. Now if you see the diagram on the right, vector A is the biggest one, then vector B, and a sum of those two vectors is even smaller than themselves. So the magnitude is very important also, but the direction is determining that sum of those two vectors when we add vectors together. We can say, we're going to talk about this later on, we can say that in a second diagram, we can represent the second diagram as a minus b as well, because two vectors, we can label them as a vector a, for example, and vector minus a if they are at the same magnitude but at the opposite direction. In this case, vector b and minus b are drawn with a black on a first diagram and minus b on a second diagram. So direction does matter, and it produces a different result as different directions are applied. So it will be very helpful if you refresh your knowledge about vectors, and some knowledge are at the end of the textbook. You try to read those time after time. However, I'm going to try to explain in a very detail what you need to know about vectors. As we study vectors, and we use those vectors a lot in chapter 1, chapter 2, 3, and 4, so the first 2 units, and this is repeated on grade 12 as well. So direction matters. Direction is a very important component of the vector. So direction is the line an object moves along from a particular starting point expressed in a degree on a compass or in terms of the compass point, like north, west, east, or south. Sometimes we express a direction based on the expression that we use in everyday's conversation, like up, down, left, right, forward, backward, and even with a plus and minus with an x and y coordinate system. So direction are often expressed in a square bracket, and we're going to use square bracket all the time. For example, we can express 500 meters east, which indicate that object is moving 500 toward the east direction. Take a look on that compass there. There's a red arrow, which is a vector pointing toward east. And the length of the vector has to be proportional to magnitude, and we already talked about it in the previous slides. Why direction is important? Imagine if you have a phone conversation with your friend and you want to meet somewhere, and they ask you to meet 500 meters from the certain intersection. You go to that intersection, but you don't really know where to go. North of that intersection, south, east, or west. So you are going to take chances, right? If you don't have direction, you're going to take chances, and you might go 500 meters north. You're going to look around. There's nothing there. Go back to the intersection again, 500 meters backward, and then may go 500 meters, east or west or south. Still you're taking chances until you get the right position. However, if they said that we're going to meet 500 meters west from that intersection, you don't have to think about north or east or south. You go directly to west and you meet that person. So that's why the direction is important. So if you want to go to school and you are in a library or from home, that means that school have a different position relative to your location. So if you are at home, your school is 500 meters east of your home. But if you are at the library, the same school is 700 meters west of your position, west of the library. So the motion toward the same object is described differently, which depends on from the reference point where you are located. So that makes a direction very important. We're going to learn about position and displacement. Position is a distance and direction of the object from a particular reference point. So position is like a location where the object is located. Position is a vector quantity because it has a magnitude and direction, and is represented by a symbol d, a lowercase d, with a vector on top. Please do not confuse that with a lowercase d for distance. Here is an example to make it clear. What is the position of the school and the position of the library shown in this diagram? Position of the school from the reference point, which is your home in this situation because it's a 0 meter, is a 500 meter if you walk toward east. So that's why it's 500 meter east. And the library is a 1200 meter east. So if you start from your home and you want to go to the library, you have to go toward east direction, and you can move 1200 meter, 1200 meter toward east. So kinematics is about motion, study of motion. It's about moving the object. So we talk about position, which is a location where the object is located. Now, what about changing to that location? What about moving from one position to another? So that's why we study displacement. The concept of displacement is the net change in position. The symbol is delta D, which is equal final position minus initial position. Let's do an example. You see that person there is starting from the position which is initially at 11 meter west to a 22 meter east. So find the displacement when initial is 11 meter west, final 22 meter east. We can just use that formula. Delta D is equal D final minus D initial is equal 22 meter east minus 11 meter west. We have a problem here because we do have two directions that are not the same. So what we need to do is flip one of them to make it the same. Either we can make two directions, both of those directions east, or both of those directions west. In order to switch the direction, we at the same time we flip the sign in front of that magnitude on that number. So 22 meter east, in order to make it to 22 meter west, we can switch it to a minus 22 meter west. And 11 meter west, if you want to flip it to make it 11 meter east, so we can switch from minus 11 to a plus 11 east. And it will make more sense to change negative to positive. So that's what we do. We change 22 meter, we leave 22 meter east, and we change it 11 meter west to a 11 meter east by changing the sign minus to plus. So now we are ready to add them up. 22 meter east plus 11 meter east is 33 meter east. Here is an example. We have initial position 500 meter east, which is school, and final position 1200 meter east, which is library. So when we go from school to library, what is the displacement? Okay, so we do the same thing. Delta D is equal D final minus D initial. D final is 1200 meter east minus 500 meter east. Since that both directions are the same, we just quickly do 1200 meter minus 500 meter is a 700 meter east. When an object changes its position more than once, experiences two or more displacement. The total displacement of the object can be calculated by adding the displacement using the following equation. Delta D total is equal to delta D1 plus delta D2 plus delta D3, etc. Here's an example. A student walks from her home to her school and then to the library. Find the total displacement. So we have two displacement, and we can calculate displacement for each individual trip. So delta D1, which is final position of the segment 1 or trip 1, minus initial position of trip 1, plus final position of trip 2, minus initial position of trip 2. So we have 500 east minus 0 meter plus 1200 meter east minus 500 meter east. So if you see the 500 meter east and minus 500 meter east cancel, and we're left with 1200 meter east. However, total displacement can be calculated just a difference in position of the end minus position of start. So no matter where you go through many trips, what matters is where did you start and where did you end up. So where is the end position of the object and minus start position of the object. To make it clear, so when you start in the morning from your home, you go anywhere during the day. However, at the evening, you go home again. So you start and end that displacement, that many trips during the day to the same position. So that means total displacement for the day is end position, which is a home, minus start position, which is home. So that's why total displacement for entire day for you that's starting from home and ending up at home is 0. So that actually is a wake-up call for you to understand that displacement is not about how long you are traveling. It's about change in position. Start position, end position, those two are what matters. Now, if we have to review back, what is a distance is a total length of path traveled. Now, displacement is about start and end, change in position. So here is an example. A student walks from her home to her friend's house and then to a grocery store. Find the total distance traveled. So if you see that total distance travel matters any direction that you go. 2.1 plus 2.1 plus 4.3 is 8.5 kilometer. Now the same example is to calculate displacement. So a student walked from her house to a friend's house, then back to a grocery store. That means it goes from your house, from her house, to a friend's house, back to the house, back to and toward grocery store. So we have 3 trips there. So one is a negative 2.1 because it goes from your house to a friend's house, opposite direction of the positive. And then from a friend's house to your house, that's another 2.1 kilometer, but this time is a positive direction because it is the direction that we have here, a positive direction. And then from house to a grocery store, that would be a positive 4.3 as well. If you see a 2.1 and minus 2.1 and plus 2.1 will cancel each other. So what is left is plus 4.3 kilometer. However, if you take a look, where did you start and where did you end up? You start from your house and you ended up to a grocery store. So that means final position minus initial position for entire trip. That means is 4.3 kilometer. So just to summarize, total displacement for that entire trip is 8.5 kilometer. However, displacement is plus 4.3 kilometer. So you can try yourself now. You can pause the video and try to calculate total displacement and total distance. So a student walks from her house to a grocery store and then to a friend's house. Find the total displacement and total distance. You can pause the video and try it yourself. Then, if you get the total displacement of minus 2.1 and total distance of 10.7 kilometer, then you understand the concept. Now, as we already mentioned, the distance depends on a path taken, so every meter counts. So distance is a scalar quantity, the direction doesn't matter. The displacement does not depend on a path taken, but is just 2 points. There's a change in that position from final minus initial. So the direction of that displacement is from initial to final. That's why it's a vector quantity. So it's a vector that joins start toward end. Now, magnitude of displacement, since that is a straight line, is always equal or less than a distance. There is no way that magnitude of displacement can be longer than a distance. So we can say absolute value of displacement is always less than equal than distance. Now, I label distance as a delta D. The reason that I label that as a delta D and not D is that sometimes we interchangeably use displacement and distance if there's a straight line, if the motion is in a straight line and we know the direction, or the direction is already understood. For example, when we solve physics problems that involve, for example, car driving, we know that usually car drives forward. So we don't really need to mention it. Instead of saying displacement, we say distance or vice versa. So we know exactly what we mean. We know exactly that if the car is moving 5 kilometers toward east, that is a distance 5 kilometers because that was a straight line. Here's another example. You can pause the video and you can try it yourself. If you were to walk from home to work, what would be your displacement? So the work position is 2,000 meters west, and your home is the reference point is 0 meter. So we can do the same thing as we did before. Change in position is final minus initial. So that means 2,000 is a final where you ended up. West minus 0 is 2,000 meters west. Second one, what is your displacement if you walk from school to the market? So you start from school, which is 700 meters east, and you ended up 2,500 meters east. So you do the same, 2,500 meters east minus 750 meters east is equal 1,750 meters east. One more. You have to go to a market one evening after work. What is your displacement from work to market? From work to market. So end position is market, start position is work. Same thing, final minus initial. Final is market, which is 25 meter east minus 200 meter west. That will make, so again, we have a east and west. We have to change west to east, and that negative sign in front of 2000 will become positive sign. So 2500 meter east plus 2000 meter east is 4500 meter east. Next one. After school, you have to go to the market before returning home. What is your total displacement? Okay, same thing all over again, final minus initial. So final, you returned at home, that will be 0. Minus 750 meter east, that is equal minus 750 meter east. However, write it down, we cannot leave the answer with a negative. So what do? We flip it, flip the direction, and we flip the sign from negative to positive. So the answer will be 750 meter west. Now it's your turn again. So you can pause the video and try to practice. Imagine that you walk from home to school in a straight line route. What is your displacement? What is your displacement if you walk from your school to the library? And you went from home to the library, and after you decide to go to the mall, what is your total displacement and the total distance? I hope you understand how to calculate distance and how to calculate displacement. What is the difference between one or the other? And by practicing, you should be able actually to understand the concept and continue with the next step in physics. The last thing that we're going to talk is about the vector scale diagram. So a vector scale diagram shows the vector associated with a displacement drawn to a particular scale. Obviously, when we draw displacement, we don't have the huge paper to draw a 700 meter west vector or 500 meter west vector. So we can add those two together and we get a total displacement. Definitely, we need to scale this down. So we can use a scale 1 centimeter is equal to a 100 meter, represent 100 meter. So we can draw delta D1 as 7 centimeter, and other one 5 centimeter. So we can draw a total where the first start, the tail of the first, toward the tip of the last. That is a resultant. Remember that when we have 2 points and we join it with a straight line, that is not a vector. That is a segment. The vector has to have a tip, has to have the direction. So what we do is you add tip to tail when we add vectors. We talked about that at the beginning of this lesson. So that was just a review. Thank you for your attention, and see you next time.